Though tentative, the IPCC, Union of Concerned Scientists, and other organizations are coming to the realization that keeping existing nuclear power plants is required if we want to mitigate the damage from climate change. The IPCC and eminent scientists like James Hansen and Ken Caldera are certain that we must expedite the requisitioning and deployment of nuclear power plants.
The examples of where we've been able to install carbon-free energy rapidly, the fastest examples are all nuclear power. When a country like Sweden decided, okay, we need to phase out carbon energy, they built 10 nuclear power plants in Sweden, a couple in Finland, but they did it in about a 10-year period and completely decarbonized their electricity. That's what we have to do.
When we contrast the combined yearly additions of low-carbon energy sources against the 150-year head start carbon-based energy sources have, things look bad. We have barely crested the first pebble at the foot of the carbon mountain. It's that bad. One of the problems of Western nuclear developments is that these are projects rather than products. None of the EPR or AP1000s that were built in the West had a finalized design at the beginning. Requirements kept changing during construction. This meant that there was a need for reassessments and delays that have cost a lot of money. Eventually, these reactors took a long time more to build than initially thought, and this casts a shadow on the industry. So how do we turn this around?
I don't know, do you want to say anything more on that?
Sure, I'll add something. In terms of the price of energy, Jim's right. You cherry pick the price of the electricity being generated by the wind turbine when it's generating electricity. When wind isn't subsidized, nobody builds it. Warren Buffett said it's not worth doing without the subsidy. Again, don't take my word for it. Just see if those wind turbines get built without that subsidy. The way you make nuclear cheap is you build the same kind of reactor over and over again like the Koreans did. Why didn't they do that in Britain? Because the anti-nuclear movement stopped them from doing it. So then you guys come around and say, well, why is it expensive? Because they have lost the experience building the plants thanks to the anti-nuclear movement.
It turns out that we have had the answer for ages already, and it is called the assembly line. But can we translate this to reactors? I think it is possible for multiple levels and multiple types of reactors. First, consider the contemporary EPR and AP1000. There's no reason to keep building these on a per-project, individual design basis. We should completely finalize the product. The only variable for these products are the possible groundwork and the cooling system. But there's no reason why they should impede manufacturing components for these reactors. Once you have your design specification for your product, mass production of components can begin. Think about pipes, pumps, breakers, railing, wireframes, you name it, but also larger components. The aim is to get as much of the reactor facility built on an assembly line. The assembly line is a force multiplier for construction speed. The adoption of assembly processes in the nuclear industry will help lower construction times significantly. Construction projects become much simpler. This is the product. This is your blueprint. This is the kind of foundation you have to lay. This is the kind of cooling required. Build that and we'll drop in our components and finish up. I know this sounds rather simplistic, but it is the truth. Want to cut down building time from 10 to 5 to perhaps even 2 years? First, standardize your product. Determine your roadmap up front. Don't allow any alterations to the product. Work with experienced people. And finally, the force multiplier. Manufacture components and reactor cores on assembly lines outfitted with robotics. Yes, that's right, reactor cores. Contemporary pressure vessels cannot be made on an assembly line. You want as many components, including the core, to be cut, welded, and tested automatically. The molten salt reactor is one of these designs that can be built that way. The molten salt reactor basically is a stainless steel or nickel alloy can with or without a solid moderator. The reactor core can be cut, rolled, and welded automatically. The moderator can be created automatically. The pumps can come off an assembly line. The piping can be cut, rolled, and welded automatically. Flanges, the same thing. This is how it works in the shipbuilding industry. This is also how it works in the airplane industry and the car building industry. All of those products, believe it or not, are a lot more complex than reactor cores. Do note that we have multiple factories completing multiple highly complex jetliners each day. Molten salt reactor cores and their ancillary devices are simpler and smaller. Here are some prime candidates for this new way of working. When can we expect to get this far? I think that it can be done within a decade. Expect the first finished products to arrive mid-2020s, and expect manufacturing capabilities to come in a couple of years later. The most important step after finishing the first reactor will be building the assembly line and securing the required supply chain. I do think that the future is bright because we can do it. But let's get going.